Welcome to this next tutorial, and today we're going to be looking at a subject called FIFO buffers, first in first out buffers. Sometimes they're called a ring buffer or a circular buffer, and these are used as a way of controlling data, moving it around from one place to another. They're a little bit of a difficult subject to visualize, so I'm going to try and give you an example. So on a recent project that I'm working on, I have got a whole set of sensors that are being read constantly, and those sensors have to send out a value over Wi-Fi. Now obviously the values can only be sent out at a certain speed, and it's sometimes during the process a whole load of data will come in as a clump of data. Now I can't process the data as quickly as it's coming in, so I need some kind of buffer to store all that information, and of course I want it kept in the right order, first in first out, so that the information is transmitted in the right order. So these are a bit of a weird thing to explain. They are based around three elements, and if we look at this screen that I'm going to switch to now, this screen we see a visualization of a FIFO buffer. Now the way that I'm working this, there are three elements. There is, down the center we have an array of data. Now in this particular array I've only put 12 elements. In the code you'll find the array has 100 elements, but it would have been a long image. And then we have a write variable and a read variable, and what is happening is as a piece of information is coming in, we're writing to a different position in the array, and then at the same time, when there's time in the program, it's also reading through the positions in the array. Now it probably sounds more complicated to talk about than to look in the code, so let's switch straight over to the code. So in our first example, I'm just going to go through the sketch. It's FIFO version 1, and these are the three variables. We've got the read position, the write position, and in this case a FIFO buffer that is 100 elements. Now I'm using an integer for each of these for this particular example. We'll see some other options in some later sketches. Now as well as that, I've got these variables here. These are nothing to do with the FIFO buffer. These are just a way of helping me to write a sketch that can help you visualize what is going on. So this sketch, there's no wiring. You can just plug your Uno board in or whatever. In fact, an Uno is probably a very good board to use for this sketch because it will show you some of the problems with a FIFO buffer. So going through the setup, we're starting the serial. I'm just printing out some information, and then we start to see the beginning of the FIFO buffer being used. Now I'm working on a project for model railways to do with LocoNet and transmitting that data over Wi-Fi. That tutorial will be coming out soon, but this is, if you like, a sub-tutorial that goes towards that. I didn't want to fill this sketch with lots of other information. Let's just stick to the FIFO buffer. So we have an array with 100 elements. Now with a FIFO buffer, if you like, there's information being written to this buffer and read almost at the same time. Obviously not exactly the same time, as we'll see, but what I wanted to do to make this easier to visualize, in the setup I have populated the first 30 positions, and all I've done is, for those who don't know, I use the letter Q a lot. That's because I'm a lazy programmer and the Q is top left on the keyboard and it has no meaning, it's just a counter, so I just use a Q. When I'm using a variable that's actually important, then I give it a name. So we've got the FIFO buffer, and it's going to write to the right position. So if we go back to our image, the right position is incrementing and working down the array. So let's get back to that code again. So we write to the FIFO buffer, and I'm just putting a value of Q in, and then we increment the right position so that next time this is called, it writes to the next position down the buffer. So it's doing that for the first 30 positions, just to give, if you like, the read a head start. Now we're going to come into the main loop here. I'll just try and explain this. I store a variable called current millis that is giving the current time in milliseconds since the board started. When you're using something like a FIFO buffer, if you use the dreaded delay, and for those who don't know what that is, let's just type it in. Delay usually looks, you'll see it written like that in code. That's delay for 1 second. If you use delay in this code, you will destroy the whole system. Delay is not something that you want to use in your code if at all possible. So we're using current millis to control this, and the way this works, there are two things that are going on. I've slowed this down as much as I can so that you can visualize it. In a normal project, everything that you're going to see within this sketch would probably happen in less than 0.1 of a second. So watching the serial monitor, your eyes would go blurred. Also, in a real project, I'll be blunt with you, do not use serial print or serial print line. These two here, comment them out for production work because it takes time to send this data to the serial monitor. And when you have a board that is in production, so for instance on my model railway, when I've got a board that's installed, I'm not reading anything off the serial monitor because it's bolted under a baseboard. So get rid of these because they can slow your code down tremendously. So using the standard like state machine style code, if the current time in milliseconds minus read millis is greater or equal to 1000, read millis is a variable that I've set here as a timer. You can see I've got write millis as a timer, and also I've got an integer random write timing, which I'll explain in a minute. So I then reset the read millis to the current millis, and so basically once a second this system is going to read a value and print it to the serial monitor. Now on the project I've been doing, it's not printing it to the serial monitor, it's transmitting it over Wi-Fi. But if you can imagine, just as we were writing to the FIFO buffer, this time we are reading. So we're printing out the value that is found in that position. So if we're looking at a diagram, we've got the first buffer that was writing, now we're reading down, and we're going to keep incrementing. And the idea is that this read has got to catch up with the write. Now that is very, very important when you're designing this sort of process. If the read cannot catch up with the write, you are going to have a disaster. Because what will happen is, if you can imagine, if this keeps writing, because it's a loop, it then goes back to 0. Now, if it gets to the point where it overtakes the read, you've got a problem, because all of a sudden this data is being overwritten and it's never going to be read by the read system. So when you're working with a FIFO buffer, one of the important things is to make sure in your code that the read has an average read speed and transmit, or what the data is worked on, quicker than it is written to. So what we're doing here is we're serial printing the position to the FIFO buffer. I've put an R in front so that I can distinguish it from the write that you'll see in a minute. We then increment the read position. Now, one of the bits on the buffer, as I said, when we get down to the bottom, we need to jump back to the top. If we go back to our code, if you remember at the top, our array has 100 elements. Now, an array of 100 elements is 0 to 99. So as we are going through, as we keep incrementing the read position, eventually we're going to come to 99 and we're going to increment it by 1. That would take it outside of the range of the array. Bad news. So what we do is, if the value gets to greater than 99, we reset the value to 0. So at that point, it's like in this one, it would be once it's got to greater than 11, go back to the beginning and start reading again. Now, to generate some values coming in, what I wanted to do was generate values coming in at random intervals. So this version, it's got a random write timing. I'm not going to explain all of this too much at the moment because it's not part of the FIFO buffer, it's just how I'm writing it. But if you like, it is causing values to be written at random intervals between half a second and 2 seconds. So if you notice, the average value that's going to come out of there is going to be what, 1.25 to 1.5 seconds, whereas we are reading once a second. So this is actually going to be writing to the values being written to the buffer are going to be slightly slower than the speed they are going to be read. So our read pointer will eventually catch up with the write pointer. Now we don't have to worry about it catching up because in the code we deal with that as well. Now where are we? So there we are. This is where we deal with it in the code. So it's only going to read from the buffer if the read position is not equal to the write position. Notice it's not equal to, it's not greater than or smaller than, and the reason for that is if right now the read position is smaller than write, but if this drops off the bottom and starts going up to 1 before this has got to the bottom, all of a sudden this value is smaller than the read value. So and that is why it needs to be a case of they are not equal rather than greater or smaller. Just one of those things you need to understand. So this is going to read once a second. It's going to check this little function, but it's only going to do something if the read position and the write position are different, because at that point it knows it's not caught up with the write position, so there's more data to be processed. So this bit down here, it's putting it in, and you'll see on the serial monitor that it's putting in a W for entering values, and as it's reading values you will see this R. So let's look at the serial monitor. We see that we start off, we've loaded our first 30 values. We can see it's reading position 0, position 1, but it's now written another value. Read another couple, now it's written 2, read 1, and so on and so forth. And as you can see, it's reading and writing. The goal of this is that the reading will always catch up with the writing, because obviously our ideal position is for this read to be one step behind the write, preferably getting to the point where it actually catches up, but sometimes that's just not possible. but you want it as close to this as possible. So going back to our system, we started off 30 apart, and now if we look, we're about 20 apart, and it will continue. Now you'll notice that the right numbers are getting quite high now, 85, 86, 87, and if you remember, this array only holds 100 items. So when we get to the top, there we are, 95, 6, 97, 98, 99, 100. And at that point, right is put in value 100, it's gone back to number 1 again. And if we now continue this, we will see the read continue in exactly the same way. Now if you're wondering why it is 1 out from the values, it's actually to do with when I write the piece of data to the screen. So but as you can see, it's running around and it's working around this buffer. So it's writing, the read is slowly catching up, and eventually we get to that point. I don't know whether it's quite got there yet. No, still not quite there. As you can see though, it's getting closer and closer. We're now only a few items apart, and the goal will be that eventually they will catch up with each other. And this brings into our next discussion, how big should the buffer be to allow this sort of thing to happen. So let's move on to the next sketch. So this is example 2, and again all of the code is available on the Digital Town website. There'll be a link below the video so you can get this. But let's have a look at this second sketch. So in the first sketch we used a value for the FIFO buffer. We had 100 elements in it. Now you'll notice this time I've changed it to 256 elements. Now you might wonder what this percentage is that I've marked afterwards. If we look down, I've just compiled the sketch, and you'll see here global variables used 732 bytes, or 35% of the dynamic memory. Now this isn't the space that the sketch is actually taking up when it's being stored to the Arduino. That's this much smaller amount, tiny amount of space has been used. This is I suppose the easiest way to think about it is this is what's written to your hard drive space. That's how much hard drive space you're using. This is how much memory, how much RAM you're using when the program is running. And you'll notice we are up to 35%. Now if I just comment this out and comment that one, we run the compiler again, he says, hoping that it's going to be quick. Yes, it is. There we go, we get an error, and the error is that it's now trying to use 108%. Now the reason this is important is obviously you want a buffer that's big enough to do what you want, but you are still limited by the fact that you will run out of memory if you make it too big. So let's go back to our 256. I chose 256 because it actually is a very interesting number to use, as you'll see in a bit. But if you can imagine, if you've got a lot of values coming in big clumps, so let's imagine you're reading from, let's say we're on a Arduino Mega, and somehow we've written a sketch that's reading from 40 pins. 40 sets of data comes in that's then got to be moved on. Maybe we're going to send it out through serial 1 or something like that, sending it over Bluetooth or whatever. But if we're going to suddenly read 40 pins, the buffer has got to be able to take all of those 40 readings, and has got to be big enough that before this might be read. So imagine it's got 40 readings. This might only have done 35 readings before the next 40 come in. Difficult one to sort of try and visualize, but you need that buffer big enough that the read can catch up with the write, but at the same time the buffer needs to be big enough to store the, if you like, the maximum amount of data that you ever think the sketch is going to need. Now I'm going to be blunt with you, sometimes you're going to have to do some experiments to figure out what's going on, but I've just left these various options in just to show you, 100 elements with an integer on an Arduino Uno uses 20% of the RAM. 256 elements, 35%. 1,000, we're up to 108. 10,000, you've gone to 987%. These values are not going to work. It's not going to compile. It just won't work. The reason 256 is an interesting value is in the previous sketch, the read position and the write position were integers. In fact, if I bring up the previous sketch, do you remember when we got to greater than 99, we dropped straight back to 0. One of the advantages of using 256 items in the array is I can make those a byte, which holds a value between 0 and 255, and that means that I can increment the read position constantly. But if I look at this little example I've written out, it will, let's say it gets to 253, 254, 255. If you are a byte, 255 plus 1 does not make 256. It makes 0, because you've overrun the space that the byte is stored in. So you get a 0 and you go back to 1 and 2. So what it allowed you to do is get rid of that little bit of code. So if your buffer size is around the 256 mark, then this is a little trick you can use if you can get it to exactly 256. The rest of the sketch is working in exactly the same way, so I'm not going to spend too much time on that one. Right, sketch 3. This time what I'm doing is using two buffers. The reason for this is, okay, it's great if you've only got one value coming in, but let's imagine we've got something, and bizarrely this is what's happened in my last project. I have a number that tells me the item number and its value that comes in. Now the value in this particular project that I'm working on is on or off. For those of you who are into your model railways, it's a block detector, so it's giving a block number and then its status, whether that block is on or off. Now what I've done here, we've got the integer value, which will hold the block number in my case, because those block numbers are never going to be greater than the range of an integer. And then the on-off status I'm just storing as a byte. Now this means that I need two arrays of 256 elements each, and as you can see, when I've compiled it, that's using 48% of the memory. Now what I'm going to do is just change that to an integer. I'm going to compile it again. And the reason for showing you this is, as you can see, it's come out at 60%. Now the reason this is important is in this sketch there are very few variables, but if all of a sudden you were doing lots of other stuff, I could get away at the moment with using two integers. Believe me, I wouldn't. I'd actually, if both of these were integers, I'd make this a two-dimensional array. But because I'm using this as a byte, I've got the two different buffers, and I can get the memory down by doing it as a byte and an integer from 60% to 48%. Now if you can imagine, if we had a few more items or these buffers were bigger, let's imagine they have to be 1,000 element arrays, all of a sudden using a byte instead of an integer becomes very, very important when it comes to saving memory space, because if you run out, you're going to have to buy yourself a bigger board. Now, in this particular sketch, we're doing exactly what we did before, writing the right position, and then I have a variable called byte swap, which I'm just switching between 0 and 1. So the 1 is going into the FIFO buffer, and the other one is the FIFO byte buffer, and it's just storing those bits of information. And that's exactly what it's doing again in here. Because I'm using 256 elements, I haven't had to reset my counter, and again we've got the same situation when we are reading the information, as we're writing the information later on in the sketch. Let's have a look at the serial monitor. Let's just restart it. So there we go. We can see it started at 30 and 1. It's on, 31 is off. Again, these were just values that I put in, just as random. But as you can see, it's the same situation, that the read system is now racing to catch up with the write system. So as you can see, this is going round and round. In my case, it's now going round 2 buffers, but it's exactly the same principle. And again, the important thing is that when you're writing your code, you write it in such a way that the read will catch up with the write. Now the write, as I've said in my last project, it's reading from some sensors. Other times this could be data that's coming in from an interrupt routine. It could be something that's coming in off a Wi-Fi, Bluetooth, even over serial communication. Just data coming in, going into a buffer, and then being processed. Bizarrely, this sort of thing actually happens in the hardware on your Arduino all the time, because when you print something to the serial monitor, obviously you send a load of data to the serial monitor, and if we think back to our code, when I write to the serial monitor, I want the W to arrive before this, and I want it to arrive before my value. If it wasn't using a first in first out buffer, this will be coming out in completely the wrong order. It will be absolute gobbledygook. So you see a FIFO buffer working when you send something to the serial monitor all the time, but now you can understand how a FIFO buffer works and how useful they can be in certain situations. They're not ideal for everything, but they're very useful for certain situations. So it's been a fairly shortish video. I hope it's been useful for you. I've done this one as a sort of an assistant to the project that's coming up next. What I like to do is any elements that are a little bit complicated in the project, I like to break out into a separate tutorial. So this is the FIFO buffer that is part of an upcoming tutorial on wireless LocoNet. So if you want to keep up with when that comes up, don't forget to click the like and subscribe. See you soon.